To continue looking at motion in one dimension, we're going to look at Chapter 2, Section 2 of your book on acceleration. Acceleration is defined in words as the rate of change of velocity with respect to time. So something could be slowing down or it could be speeding up. The average acceleration, here's another equation you're going to want to make sure that you note. The average acceleration is the change in velocity over the change in time. Remember, velocity was the change in position over change in time. So now we're looking at change in position over change in time, or velocity, and that's all going to be over the change in time. So let's look at the equation and then some examples to see how this works. So average acceleration is going to be equal to final velocity minus initial velocity over the final time minus the initial time, where now we have delta V over delta T. And remember that delta V was the change in position over change in time. Now, to make sure that we get our units right, let's take another look at this again. Delta V over delta T is meters per second over seconds. And to do the math on that, to solve that, we have meters per second over seconds over 1. So that means we have meters per second. And to divide by a fraction, we invert that fraction and multiply. So we then have meters per second over 1 over seconds, times 1 over seconds, which ends up being meters per second squared. And this is the units of acceleration. We have meters times 1 equals meters, and then we have seconds times seconds is seconds squared. So pretty simple. To look at an example, we're going to go to problem B, and that's on page 49 of your text. And this is going to show you how you will format this when you do your work. In this example, we have a shuttle bus slowing down with an average acceleration and now since it's slowing down, we're going to have a negative acceleration. So it's going to be negative 1.8 meters per second squared, units of acceleration. Negative again, negative because it's slowing down. We want to know how long it will take for the bus to slow down from a velocity of 9.0 meters per second to a complete stop. Okay. So the first thing we want to do is we want to list our variables. This is what your work will look like again when you turn it in. So we had initial velocity of 9.0 meters per second. We had a final velocity. Now, remember this says it's coming to a complete stop, so the final velocity is going to be 0 meters per second. Our average acceleration was given as negative 1.8 meters per second squared. And we're looking for the time that it would take. So this is how we will show that. Our equation, if you remember, scrolling up here, is going to be A average is going to equal the change in velocity over the change in time. The change in velocity is going to be the final velocity minus the initial velocity over delta t. Now here, our final velocity was 0 meters per second. Our initial velocity was 9.0 meters per second. Our acceleration is negative 1.8 meters per second squared. So looking at the units and the numbers, 0 minus 9 is negative 9.0 meters per second, and that's over negative 1.8 meters per second squared. So we're actually going to end up with a positive acceleration here. And the negative cancel out, which is legal. So when we do 9 divided by 1.8, we get 5.0, and then the units will be meters over seconds over meters over seconds squared, which would be meters over seconds times seconds squared over meters. Canceling the meters and canceling one of the seconds, we end up with units of seconds. So here would be your answer. That is how you do a basic average acceleration calculation.